calculus, differentiation, linear functions. Example 1. Let's consider the linear function fx equals k, or fx is a constant. So find the derivative of fx equals k from first principles. So here's a line, fx equals k. In fact, this line is the line y is equal to 3, or fx is equal to 3. All points here, 0, 3, 1, 3, 2, 3, minus 2, 3. All the points on that red line have an xy, a y value in the xy of 3. But similarly, there are lines parallel to this. That's the line y is 0, y is 1, y is 2, etc. All the lines parallel to that. So we'll now use it to get the derivative of y equals fx equals k, a constant. So starting with the formula, we can see the point xy is on this line. If we now move to the point x plus delta x, y plus delta y, we can see that by moving out a bit, changing the x from x to x plus delta x, we're still on the same y line. So the y and the y plus delta y are the same. So y plus delta y is also equal to k, because it's still on the same line. Y plus delta y minus y is k minus k. This line minus that. Now, doing some eliminations, we get the two y's cancel, so delta y is, and the two k's cancel, so delta y is 0. So the slope of that line, because it's horizontal, the delta y has not changed. So as we moved out from x to x plus delta x, we didn't move up and we didn't move down. There was no change in the y direction. So in terms of the slope, delta y over delta x, the change in the vertical over the change in the horizontal, it's 0 over delta x, or 0. And at the limit, as delta x gets small, as that gap from there gets smaller, maybe this gap, or just a small bit out, the limit is dy dx, and dy dx of that line there is 0. So any horizontal line has a slope of 0. So y is fx is k, dy dx is 0. That's if we were doing it without using first principles. We'd say if y is a constant, dy dx is 0. There's the points. So slope is 0, the function doesn't turn. That red line goes from way back at minus infinity up to plus infinity and never changes, never turns. The slope is always 0. And if the point is the first one there or the second one, either point, we can see there that where we start with our x and where we start with our x plus delta x, we still end up that the slope, the change in the y values is always 0. So, finding the derivative of fx equal to k from first principles without drawing the line and just doing the operations, we would say y is fx is k, y plus delta y, we put in x plus delta x, and that's also equal to k, because it was a constant. Y plus delta y minus y is k minus k, the two y's cancel, the two k's cancel, dy is 0, dy dx is 0 over delta x is 0, and at the limit dy dx is 0. That's how it's done. Now we'll start now with the linear function fx is ax. Here we've got a constant in front of the x, and we're doing it again from first principles. If y is ax, y plus delta y is a times x plus delta x. So where we had y, we put in y plus delta y. Where we had x, we put in x plus delta x. Multiplying in, we get a times x and a times delta x. Y plus delta y minus y is ax plus a times delta x minus the first line, ax. And now we can do some eliminations. The two y's cancel, the two terms in ax cancel, and we get delta y is a times delta x. Dividing by delta x on both sides, we get delta y over delta x is a times delta x over delta x. And they cancel. So effectively, delta y over delta x is a. And at the limit, as delta x gets small, delta y over delta x becomes dy dx, and that's equal to a. So again, if somebody said fx is ax or fx is 3x, then dy dx will be 3. If xx is ax, then dy dx is just the a, the coefficient before the x. And here we've got the example of the line y is equal to ax, the point xy, and the point x plus delta x, y plus delta y. So as we move out in the x from x to x plus delta x, we move out this distance, delta x, and for that we move up this distance, the delta y. So that's the change in vertical height for that change in horizontal distance from one point to another. So we can see that ratio of delta y over delta x. If we were doing this with the general rule, we would say y is equal to fx is ax, dy dx of ax, we would just say leave the a and eliminate the term in x. So in this case the slope is constant. Dy dx is a, that slope is always constant. For every step we move out, we're climbing at the same rate all the time. The function doesn't turn, stays in the same direction all the time. And the points there, if we use one or the other, we can see that we start here or start further down, we still get the same ratio between delta y and delta x. The slope is always a constant and the function does not turn.